All right. Hello, everyone. Thank you all for coming. Today, we are fortunate to hear from Dr. Ted Mackereth. Ted is a Banting, CITA, and Dunlap Fellow. Prior to coming to Toronto, he was a fellow at Birmingham, and before that, did his PhD in Liverpool. Ted is an expert in galactic dynamics and galactic archaeology, and I look forward to hearing what he has to say. So, Ted, it's all yours.
Thanks, Yunosh. Yeah, it's great to. I'll just share my slides, but I'll have to also add that it's expert in inverted commas as usual. Right, yeah. Can everybody see the slides there? I'm just going to bring you guys over to my window. Okay.
Yep, I can see your slides in your cursor.
Okay, great. Yeah, so it's really nice to be able to talk to you all today about my research. It's nice to do a talk in your home institute, I guess. And yeah, so I'm going to talk to you today about some work that we've been doing very recently, which I'm calling a genetic approach to constraining the assembly of the Milky Way. Hopefully this idea of genetic will come clear throughout the talk. But essentially, my work's been revolving around understanding how we can understand how our galaxy formed and evolved, and then how we can put the Milky Way into context with other galaxies and use it as a tool for constraining galaxy formation models. So we all know that in lambda CDM, galaxies form via sort of hierarchical mass assembly. So you have these small clumps of dark matter which conglomerate together. Some gas falls into those and begins forming stars. But then as that process is happening, those small clumps merge together to form even larger clumps and eventually very large clumps, which are the galaxies that we see in the universe and all of the dwarfs and satellites around those. And this mass assembly essentially determines, to some degree, how the star formation and then the subsequent feedback from stars and also the AGN of galaxies and their kind of dynamical evolution proceeds in a galaxy. So you can imagine, if you have a lot of early mass assembly, you collect a lot of gas early on, and therefore your star formation rate will be higher. And this is just one example of that in this plot I'm showing here. So this is just a schematic of the galaxy stellar mass function. And you see that the galaxy stellar mass function has this kind of characteristic mean, and there's kind of this little point where the galaxy stellar mass function has this kind of just right or Goldilocks zone, if you like. And then at the lower masses, galaxies are kind of dominated by the supernova feedback, and then at the higher masses, galaxies are dominated by the AGN or the black hole feedback at the center of those galaxies. And a lot of that is really determined by the way that the mass is accreted out of those galaxies, right? So if you're a lower mass galaxy, you're going to eject via this star formation feedback rather than the AGN, for example. So you might think, okay, then if mass assembly determines all of these things, then to what extent does a fixed mass assembly produce the same galaxy at the end of the day? And that's kind of where I want to make this analogy with genetics. And one of the reasons that I want to do that is just because genetics is just so much more 2021. We used to say we were galactic archaeologists when we studied the Milky Way, and we would say, oh, we're using the stars of the Milky Way as a sort of fossil record. But now I'm kind of, in the 2021 era, we want to be galactic geneticists. We want, and obviously this is kind of a joke, but I think this is kind of, something interesting about the way we think about galaxy formation. So galaxies form, we think, from these early fluctuations in the background density of the universe after the Big Bang. So the bigger fluctuations cause larger overdensities that dark matter that formed by the dark matter, and then the gas falls into, and you get more massive galaxies and more dense environments. And this is kind of what I would like to say is the genetics of galaxies. The sort of primordial things which are set in from the Big Bang. And then all of the other things that happen to a galaxy in the interim period, we might call it. So for example, you see that there's, somebody's got their mic on, but you see there's a lot of effects from environments of galaxies. They're in dense environments, they evolve slightly differently. I also mentioned the feedback processes that determine the way that galaxies evolve. And there's also, just many other things that can turn a galaxy from these early fluctuations into the galaxies that we see at redshift 0 or, at the present day. And those are what, we would like to say are the sort of those traits of galaxies, right? So, just like human beings have traits like blue eyes and things like that are set by our genetics, maybe there's some connection between the traits that we see in galaxies at redshift 0 and that very early primordial kind of genetics. And that's really what I want to do with the Milky Way. And that's the kind of thing that I'm trying to put forward in this talk today. So you might ask, okay, then, so what are these genetic traits of galaxies, right? And that's a difficult question to answer. It's something that I don't think we have answered yet, right? So we see, galaxies have certain morphologies. Maybe that is a genetic trait, but it seems probable that that isn't, right? We think galaxies change their morphologies when they merge and do all sorts of the secular things that happen inside galaxies. So maybe they're not very good genetic traits. We also, study dynamics of galaxies, and we look at the stellar content and the way that that is orbiting within a galaxy. But that's a similar sort of idea to the morphology, and therefore probably is affected by some of the more secular things that happen in a galaxy, or those epigenetic effects. You can also study things like the stellar population and see how the star formation history has changed throughout that galaxy, and maybe that is getting closer to a genetic trait. But the one that I'm really going to talk about today in this talk is the element abundances of a galaxy. So, we now observe for the Milky Way element abundances of at least 20 elements for hundreds of thousands of stars. So that, we're now really getting to the point where we're seeing element abundances of this very high level of detail on a sort of star by star basis for stars in our galaxy. And the abundances that I'm most interested in are these alpha and ion abundances. So anybody who's watched the talk maybe before will have already heard me banging on about this plot. But I think this is a really fundamental figure for understanding how our galaxy evolved and the way that it came to be how it is today. So you don't need to understand much about this to see already that there's when you look at these two combinations of element abundances, so the alpha over ion ratio, so the alpha elements are like magnesium, oxygen, silicon, elements produced in the triple alpha process in stars, and the iron over hydrogen ratio. So iron is generally produced from type 1a supernovae, and I'll talk about that in a minute. But just by looking at these two ratios of elements, you can see that there's something interesting happening in the galaxy, right? You see that there's these two populations of stars, such that you have a population of very high alpha over iron stars, so they have more alpha relative to the iron, and then this population is kind of low iron over hydrogen. And this is all normalized to the sun, so you can see that the sun would sit at about 0, 0 here. And we've actually known about this, it turns out, since like 1962. So I was told the other day by Rosemary Wise, who is a very good source on the subject, that George Wallerstein in 1962, unfortunately George passed away last month, so it's very sad. But he, in 1962, with photographic plates, measured the abundances of about 20 stars in the nearby Milky Way. And you can actually see that when you put his plot over the top of the apogee plot, amazingly, these two things are very consistent. But we've actually known that there's these high alpha over iron stars in the Milky Way since 1962. And we really haven't got a huge level of understanding about how this population came to be in our galaxy, or really what it means. And that's really where my research is focused. And this alpha over Fe, this bimodality, these two populations, you can actually see those pretty much everywhere in the galactic disk. So this is a plot from an early apogee paper by Michael Hayden that just shows this alpha over iron plane in different bins in galactocentric radius going from left to right, and height above the midplane of the galaxy going from the bottom to the top. So these are those highly vertically extended populations, whereas these are the populations closer into the disk. But the main takeaway here is that you can just see that there's these like two populations of stars in pretty much all of these zones. And the way that the density is plotted here is kind of making that more difficult to see. But what you can see is that as you move further out in the disk, these high alpha stars start to dominate over these low alpha stars. So there's definitely some spatial correlations with these things within the galaxy, but those two populations exist pretty much everywhere. And this is kind of a troublesome thing to work out if you're in the game of making galactic chemical evolution models, because you can't explain how to get these two timescales by just kind of these two populations in alpha over iron without thinking about the way that those elements come about. So the alpha Fe enhancement is all about the timescales of stellar evolution in the galaxy. So alpha elements, as I mentioned before, are like magnesium, oxygen, silicon, and iron, and those are produced mainly from type 2 supernovae. And type 2 supernovae occur, their progenitors are massive stars. So as soon as you form stars in a galaxy, you're going to get a population of massive stars, which are very short-lived, and therefore will explode very quickly in these type 2 supernovae and enrich the interstellar medium in oxygen and iron. But then you also have type 1a supernovae, which are the other main source of elements in the interstellar medium. And these are actually then slightly delayed. So type 1a supernovae produce mainly iron and only trace amounts of these other elements, including those alpha elements. But because these happen in, we think, white dwarf red giant binary pairs, essentially what happens is the red giant, some material accretes from the red giant onto the white dwarf, and therefore increases the white dwarf mass above the Chandrasekhar limit, and then you undergo a supernova explosion. So the time for this process to happen causes there to be some sort of delay time. So these supernovae are not going off straight away in the population, leading to there to be this kind of delay time. So the enrichment of iron into the interstellar medium relative to these these alpha elements, it is slightly delayed. What that means is you get this kind of interesting thing where at early times when you're forming stars very rapidly and these type 1a supernovae are happening in the absence of when these type 2 supernovae are happening in the absence of type 1a's, you see this enhancement of this alpha over iron ratio because you're producing more oxygen relative to iron. And you can then go back to this plot and say, okay, well, now we understand a little bit more about where these elements are coming from. We can start to unpick what these populations mean. So we know then now that these stars are those which were enriched in alpha elements before the onset of those type 1a supernovae. So they must have formed in the very early Milky Way when the gas was being recycled quick enough that only the type 2 supernovae were enriching the interstellar medium. Whereas these low alpha stars will probably form from gas that was enriched by those type 1a supernovae, because the alpha over iron ratio is approaching sort of solar level, and you can see that they're actually more enriched in iron as well, slightly, but they do kind of overlap. But you can also think, well, actually, it's very difficult to understand how this star could form once you've evolved the gas in your interstellar medium along this kind of track, right? So if the gas is somewhere over here, how are you forming stars with these low metallicities and low alpha over iron ratios? And this is something that people have tried to understand using analytical models for many years. So in 2001, Christina Ciappini came up with a model called the 2-inflow model, which says that, okay, maybe you form these high alpha stars with this rapid early star formation, and then you have a quenching episode with pristine gas, which is not enriched, inflowing onto the galaxy, and then you form this low alpha track with a later star formation, which from the gas which was sort of mixed between this pristine gas and the gas which was still remaining in the galaxy after the formation of this event. This quenching event, we're not really sure how that could have happened, or whether it was because the gas was exhausted or something was going on in the galaxy. And so this is just like an analytical model that can kind of reproduce this. A second sort of version of these analytical models is what I like to call the sort of radial migration type models. And these were sort of pioneered by Ralph Schomrich and James Binney in 2009. And this suggests that if you have a parallel star formation occurring in the disk with a varying efficiency of the star formation as a function of the radius. So in the inner disk, the gas density is higher, star formation efficiency should then be higher. In the outer disk, the gas density is slightly lower, so the star formation efficiency is then lower, and you get this gradient of star formation efficiency as a function of radius. And what you would see is that stars would form along tracks that look something like this, where you've got the inner galactocentric radii becoming enriched faster than the outer galactocentric radii. And then this paper suggests that you could form stars along those tracks and then mix those populations all together in a radial sense. So you're then kind of mixing them all together, and then that's why you would see, for example, at the sun, these two populations kind of superimpose one another. And this is all really useful and tells you something about what's going on here, but the predictive power of these models is actually quite limited by the informative sort of inputs that you put in them. So, they all impose things like an episode of gas inflow or this kind of stellar radial migration. And it's probably looking likely that there's actually some combination of these things that produces this interesting alpha Fe boundality in the Milky Way. So when I started my PhD, we were at the stage where we were really thinking that we actually needed to start making models that could predict this ab initio without input of these kind of gas inflow, radial migration, and things like that. And that's where the Eagle simulations came in my career. So the Eagle simulations are actually looking quite old these days. These were done in about 2015, and they're a large volume cosmological simulation, so 100 megaparsecs, simulated self-consistently. So what that means is that it's just a big box full of gas and dark matter, and you evolve that with some subgrid physics, and you hope that your galaxy population at the end comes out looking just right. And to do that, in order to get the galaxy population looking just right, you use an observable. For example, in the case of Eagle, you use the galaxy stellar mass function, and you just tweak the knobs of just some parts of the subgrid physics model that determines like star formation or feedback. And you tweak those knobs until you match that kind of galaxy stellar mass function. And then you hope that all of the other observables of your simulation are actually then predictions for the observables of the real universe. And it just so happened that in Eagle, they have about 133 Milky Way-like galaxies within the sort of stellar mass range of the Milky Way, which are actually disk dominated. So this is the Hubble tuning fork that you get from Eagle. You can pick galaxies out of the simulation, but relatively like galaxies we see in the real universe. course, like I said, this is now looking quite old. If you look at the more recent simulations that are at high resolution, you can see all sorts of interesting features. But one of the best things about Eagle was, for me at least, was that they tracked the evolution of 11 elements, including some alpha elements, in order to do the radiative cooling calculations. So gas in the simulations needs to cool to form stars. And in order to do that, you need the line cooling from metals. And so in that case, you need to sort of self-consistently evolve the element abundances. And that's what they did with Eagle. So I was able to go and look at this sample of 133 Milky Way-like galaxies and look at its alpha over iron planes, because it was all simulated for me in those simulations. So this large volume of simulations essentially allowed us to look at the statistics of this alpha Fe boundarity in the simulations. And you can see that broadly, these are just 3 examples of those 133 galaxies. But you can see that broadly, you see this huge variety of different alpha over iron planes. So this is just like the Milky Way plot that I showed before, but now you're seeing galaxy to galaxy variations that make this look extremely there's a lot of variance in these galaxies. And in particular, we found a bunch of galaxies that do seem to have these kind of bimodal alpha to iron ratios. So it doesn't look exactly like the Milky Way, but you see that at fixed metallicity, you get 2 peaks in your alpha over iron distribution. So we looked at this and we thought, well, okay, this must mean that something is happening in the simulation that is representative of what's going on in the real Milky Way. And the other thing you can do is look at things like how often these types of galaxies appear. So these were the 3 sort of main types that we saw amongst our sample, and we saw that 60% looked like low alpha only, so they didn't have that high alpha track, just a low alpha. 15% had a high alpha only, with not really much evidence of a low alpha track, just a few stars kind of peppering that area. And then it was actually only 5% of the galaxies that had this bimodality. So this feature, at least in the Eagle simulations, is already looking quite rare, which is interesting in itself. But that's not really what I'm going to focus on in the talk today. I'm actually just going to focus on how this feature arises in the simulations and what I think that means for the Milky Way. So we see that Milky Way-like zoom simulations also have this feature. So when people do more higher resolution simulations where you isolate a single galaxy from these cosmological volumes and then simulate again with a lower resolution region surrounding them, but this very high resolution region, you see that this alpha bimodality comes out in a lot of those. So at high resolution, you do see this effect. And this, in these 3 papers I've just highlighted here, but there's a couple more as well now, were attributed to a variety of different processes within the galaxy. So I think in this paper by Oscar Agert, they said that there was maybe a gas-rich merger that kind of caused there to be these 2 populations. This paper by Rob Grant, they said something about high-density star formation in the center of the galaxy. So that's looking more like that kind of star formation efficiency gradient kind of scenario. And in this paper by Buck et al., I think they were also saying something about very highly efficient star formation at early times, forming these high alpha stars. So you do see this in these Milky Way zoom sims, but of course you don't get the statistical. You can't do the statistics like we could in Eagle. So because we could do that statistics, we could look at something interesting about the way that whole population of galaxies that had that bimodality, so that 5% of galaxies evolved relative to the rest of the galaxies in that sample of 133. And we were able to look at things like the mass assembly histories, and this is what I thought was the most interesting result from that paper that I wrote in 2018. What we found was that when we matched the halos in the simulation at redshift 0 to the halos in a dark matter only simulation, which is exactly the same as Eagle, except it doesn't have any of those baryonic effects, and then looked at the mass assembly histories of the galaxies that were bimodal and also just the rest of those disk galaxies, and compared them to an analytic approximation to what we expect the assembly history of a galaxy with this mass at redshift 0 to be, we found these bimodal galaxies actually have their mass assembly offset from the non-bimodal galaxies, such that you see that they have this kind of early rapid accretion of dark matter at early times, but then they kind of slow down later on. And what this means is that the bimodal galaxies end up having slightly higher halo masses at redshift 0. But even when you match those 2 samples and you take the disk galaxies with the same redshift 0 halo mass and compare them to bimodal galaxies, you still see this interesting kind of offset, such that the bimodal galaxies are defined by galaxies that have a very early assembly history. But the real question that I asked at the end of writing this paper was, well, how do we show that this was the fundamental driver? So how do we show that this mass assembly thing is really what's causing the physics of those galaxies to change? And that's really what I've been focused on for the last couple of years with the simulations that I'm going to show you today. You could also do something like zoom out a little bit in the simulation. So we just make a wider selection of Milky Way mass galaxies from Eagle, and then looked at the statistics of bimodality in them. So you can see that we found a whole lot more bimodal galaxies. So that the fraction is still about 5 to, I think it's like 8% in this case. It's like a wider selection of galaxies, and this time not selecting on diskiness as well. But you see that the general picture that these bimodal galaxies tend to form earlier holds true. So what I'm showing you here is the redshift, at which a quarter of the total redshift zero mass is in the main progenitor halo. So this is like some sort of statistic of the assembly history versus the scatter in alpha elements at redshift zero at metallicities higher than about minus 0.5 dex. So what this kind of tells you is, how wide is that alpha to iron plane? And for example, in galaxies which have a bimodality, this would be very wide, right? Because you'd expect that it's not really modeled very well by a Gaussian, right? So the sigma over oxygen over iron would be higher. And you can kind of see, yeah, okay, this picture holds, right? So the galaxies with the bimodality seem to form a little bit earlier in terms of this Z quarter number, and they definitely have higher scatter in their oxygen over iron ratios. There's a whole load of galaxies here that are non-bimodal that have those same characteristics, and there's a huge amount of scatter about this relationship. So just to summarize up to here, I've said quite a few things, so I just wanted to have a quick summary. So I've shown you that the Milky Way has this alpha over iron bimodality at fixed metallicity. Forming those high alpha stars requires this high efficiency star formation in your galaxy, right? So to get those higher alpha to iron ratios, you have to really be turning over the gas in your galaxy very quickly. And I've shown you that simulations do reproduce this bimodality, and Eagle predicts that bimodal galaxies assemble early on average. But there's a lot of scatter about that prediction. And I mentioned that we really wanted to figure out whether this early mass assembly history was really a fundamental predictor of having a bimodality. It seems like maybe that isn't the case, and that's kind of how I ended up doing the work that I'm going to really present to you today. So this is where this genetic idea comes in. So genetic is this code developed in UCL by Andrew Ponson and his group in this paper by Stephen Stopper. Describes the code, and essentially it's a way of generating initial conditions for your simulation that allows you to make these modifications to the underlying density field of those initial conditions, which allows you to modify things like the intensity of mergers, or for example the assembly history of your galaxy. So this plot kind of just demonstrates what this algorithm does. Essentially you take an original dark matter only simulation or an original hydrodynamic simulation. You can mask out a kind of zoom region. So this would have started off, this is all at redshift zero, right? So this would have started off as being a sort of spherical region of the initial conditions, which then evolves to become very non-spherical due to the non-linearity of the way that the galaxies evolve in the universe. But you can see that by doing a kind of zoom in here, the resolution of this section increases relative to the original simulation. And then you can also then select things like a set of particles from that initial fiducial zoom simulation, go back to the initial conditions and enhance the initial density field such that the modification allows you to then change things like the mass of a galaxy at redshift zero, or indeed fix the mass but change the assembly history. And that's really why this algorithm was so important for this work, because we wanted to do things like test how changing a galaxy's assembly history can change its eventual alpha over iron ratio. And I'll get into that in a little bit. Just going to kind of run through a few more details of how that algorithm works. So in our case, we wanted to just adjust the assembly history and not change the mass of the galaxy at redshift zero. So our own simulations look something like this. So this was from a paper by John Davies, who's a postdoc at UCL and who I'm working with on this project as well. And he was interested in studying how the AGN feedback in galaxies was affected by the assembly history. And actually, it turns out that those simulations were extremely useful for doing the same work that I was doing in terms of understanding how the mass assembly history affects the eventual alpha to iron ratio. So this kind of just demonstrates what the genetic algorithm does in this case. So this is the redshift 2 distribution of mass in those galaxies versus the present day distribution of mass in the genetically modified galaxies, with this organic case in the middle, which is kind of like the fiducial simulation that you run. And then the early and late versions of that galaxy. So early being, we've adjusted the assembly history so that it was much more, so the assembly history was earlier, so that Z quarter, if you like, would be at a higher redshift. And in this case, the GM late simulations are where we push the assembly history to be much later, so that that Z quarter would be a much lower number, a much lower redshift, right? what you can see is it really just changes the way that the mass gets into that galaxy. So in the GM early simulation, you can see that at redshift 2, there's a lot more mass in the same radius than in the late forming galaxy, which has a much lower critical radius and is much sort of more quiescent in terms of the amount of mergers that are happening and the number of subhalos that are in that galaxy. Whereas at redshift 0, you can see that the galaxies pretty much look the same. You know, the distribution of mass is pretty much the same. They have similar sort of numbers of satellite galaxies. So it's really changing things early on, but keeping things fixed later on. The masses of these galaxies at redshift 0 are very much the same. Whereas you can see that the mass at redshift 2 is very different. So this is a great way of testing how you can fix everything else apart from the assembly history in a galaxy and see how that affects it. So I went and looked at the alpha Orion planes in this galaxy, and it turns out there's a whole lot more simulations than just those 3 that I showed in the images. There's actually a whole grid of different assembly histories, but also different random seed variations. So you can actually take that one galaxy, so this is the fiducial galaxy, and you can look at a whole grid of galaxies with different of different simulations of the products of different simulations with different random seed variations and different assembly histories. And by random seed variations, essentially what I mean is that we have the same initial conditions, but change the random number generator seed in the code for Eagle. So these are all run with the Eagle code, except changing the random seed, which governs things like the stochastic processes in the simulations, like star formation and feedback. So, and what you can see immediately is that although the assembly history and the initial conditions are fixed, these random seed variations cause lots of differences in the alpha to ion planes of the galaxy. So even though these simulations are all run from the same set of initial conditions, the outcome is very different in all of these galaxies, and that really is dictated only by this random number seed. And I'll get onto that a little bit later, but I just wanted to point out really here that the main effect you can see is that as you move, so if you just marginalize over all of those distributions, and as you move from a very early forming galaxy to a very late forming galaxy, you can see that there's this clear trend where these early forming galaxies are dominated by very sort of high alpha only tracks, but also some bimodal galaxies, moving into a population of galaxies with different random seeds that are all pretty much bimodal, into the organic, which was kind of ambiguously bimodal, and then moving closer and closer to being just a unimodal low alpha only. So it really does seem like this alpha of Orion bimodality is more readily seen as the galaxy assembles earlier. And you can link that in the simulations back to the physics of those galaxies, right? So what I'm showing you in these plots is just how different properties of the galaxies change as a function of time for that early forming case and the late forming case, and also that organic case. So the organic case here is in orange and the late former is in blue. But really, I want you to concentrate on that early form to understand really why that bimodality comes out in those galaxies. So, of course, we put in the early mass assembly in these galaxies. And as you can see, because we ran these at very high time resolution, there's a lot of variation in the mass as a function of time, because these galaxies are having quite violent histories, right? But that early mass assembly triggers an early gas inflow. So this is the radius of gas, of the mean radius of gas particles as they fall into this galaxy. And this dashed line just represents about 30 kiloparsecs, which we define as some sort of radius for infall onto the galaxy. That's just the simplest way to do it. And you can see that this gray line showing the early assembling galaxy, you can see that the gas just falls onto that galaxy much more early. So this is about 3 gigayears into the simulation. Most of the gas is already into that galaxy. Whereas in the late former, the gas inflow is much slower, and most of the gas doesn't get to the galaxy until about 10 gigayears into the simulation. So these early gas inflows are really dictated by this mass assembly. You can see that the timescales of those two things kind of match up. You can then look at things like the cooling timescale or the gas consumption timescale. So this is essentially like the mass of gas particles in the simulation divided by star formation rate, which gives you a kind of timescale for how long a gas particle can remain in the ISM of that galaxy before it turns into a star particle. And you can see that this gas consumption timescale really gets driven down. So as you see this early gas inflow, the gas consumption timescale actually goes down to very low values. So about 1 gigayear is where you'd expect to see gas particles turning into star particles before the type 1a supernova ejecta happens. And that's really what you can see in this galaxy, is that as that early gas inflow happens, this the gas consumption timescale is really driven down to values which are well below the timescale for type 1a supernovae in evil simulations. And similarly, you can see that happening in these other galaxies. The late forming galaxy undergoes this kind of slower gas inflow, which reflects itself in the gas consumption timescale profile as a function of time. You can see that it really takes a long time to get to the point where it's forming stars efficiently enough that you wouldn't see the ejecta of those type 1a supernovae. And you can see, and so what that means is that the gas particles in this late former are turning into stars really after a lot of the ejecta of type 1a supernovae has already polluted that ISM. And you can see that as well in the star formation rates, right? So the star formation rate in this early former does pick up before the gas consumption timescale really gets below that timescale for type 1a supernovae in that galaxy. And you can see as well that this early forming galaxy, that very rapid reduction of the gas consumption timescale is then accompanied by a huge increase in the star formation rate of that galaxy, which is really where most of those high alpha stars are really forming. And in the organic case, you kind of see that come a lot later. So it's really all about the timescales, and you can see that happening in all of these different cases, that the mass assembly is really dictating the timescale of these events in the galaxy's history. And then the final thing you can look at is the oxygen of Orion of the gas. And you can see that this very early rapid increase of star formation rate in the early forming galaxy, or the early assembling galaxy, really is also accompanied by an intensely rapid increase in the oxygen of Orion ratio of the gas in that galaxy. So all of the stars forming here have very high oxygen of Orion ratios, or alpha of Orion ratios, whereas the stars in this galaxy, the gas in this galaxy just really doesn't ever reach those kind of high oxygen of Orion ratios that you need to form high alpha stars. And that's really how I think the assembly that we've put into these galaxies that we've controlled for is actually causing the physics to change inside the gas of those galaxies, and therefore changing the way that the abundances of those galaxies looks. Okay, so this is all good, but I showed you that there was loads of stochastic variation between those galaxies. So at the early assembling case, you saw that those alpha to ion planes look extremely different to one another. So what's going on? Why do you get those stochastic variations? Well, I think this is something to do with the way that the feedback happens in the simulations, right? So we knew that all of those different seed variations, the random number generated seed variations could cause the random number generation in evil to happen in a different way, right? So if you have, for example, you roll the dice to see if you're going to undergo some sort of feedback process, that would happen differently in all of those different realizations. And what you see in those galaxies is that the variance, or the seed to seed variance, so this is the variance in those different planes of the alpha, in those different alpha to ion planes. So each pixel here represents some number of star particles in the simulation, and we essentially just sum up the variance of these seed to seed variations. Has an extremely strong correlation with the time at which a quarter of the mass is assembled into those. So that's that T quarter coming in again. So you can see that those early forming galaxies just have way more variance than the organic case. This is all expressed in the difference from the organic case. But the other thing you can see is that this is also some correlation with the black hole mass, right? So these early forming galaxies just have a very much more massive black hole. And what that means is that those galaxies, because they're early formers, the black hole just accretes more mass at early times and is therefore much more eligible to undergo feedback at early times. So what's happening is in those early forming galaxies, the black hole is just getting into a stage where it can actually start really pumping energy into that galaxy. And therefore those galaxies become eligible to just lose a lot of their gas. So what happens is that as those stars are forming on a high alpha sequence, the black hole's really sort of charging up. And in just a few of those cases, the black hole really ejects a lot of that gas. And you might think that this is some sort of like the inconsistency with what's going on in the Milky Way, right? We know that the Milky Way has a kind of low mass black hole. And this is something I find really interesting, is that when you look at the galaxies which have the alpha bimodalities, they seem to scatter low in terms of the black hole mass. So it seems like if you're just lucky enough that you haven't fed the black hole enough because of the dynamics of the gas in those simulations, you can become more eligible to become bimodal in redshift 0. And the best way to kind of show you that happening in the simulations is just by looking at images of these galaxies after they've formed their high alpha stellar populations. So I've just got the pictures of these two examples of those galaxies with early assembly histories. And I've picked a case which was non-bimodal and a case that was sort of clearly bimodal. And if you just look at the snapshot just after those galaxies have formed their high alpha stars, so they've all formed these stars by this point, and you just look at a slice in temperature of the gas surrounding that galaxy on a very large scale, actually, right? you can see that the non-bimodal case has simply ejected all of that cold gas, whereas in the bimodal case, there seems to be this kind of cold gas reservoir that's still existing in the galaxy after it's formed its high alpha stars. Whereas this galaxy has, kind of a hot gaseous halo, which indicates that it's kind of just punched out all of that gas because the AGN, for example, has just turned on and deposited energy into the ISM in just the right way that gas was able to be ejected from the galaxy. And you can see that this kind of disrupts as well a lot of the larger scale inflows that happen into that galaxy, whereas in this galaxy, you've kind of got a lot more cold gas able to access it. So what that means is that the bimodal galaxy can actually then go on and form more stars at a later time, whereas this galaxy really has kind of quenched itself and caused itself to be unable to form more stars. And that's really the kind of most visual way I could think of to show this. But of course, you could look at stuff. We have looked, for example, at the amount of energy that is deposited into the ISM, and it just seems like this galaxy really just doesn't have the same sort of feedback history as this galaxy. So that's kind of an interesting, prediction for the Milky Way. Maybe the Milky Way was a galaxy which was, able to build its black hole and have an early mass assembly history that did not really undergo the same kind of feedback events. And I think that is kind of reflected in some of the results we get. For example, in the Fermi bubbles of the Milky Way, they kind of suggest that it had kind of a very quiescent feedback history in terms of the AGN, for example. And it's really at this point that this becomes more like a CITA failure seminar, if you like, because we suddenly realized that maybe, this wasn't quite realistic, right? So what happened is that we, in these genetic simulations, we picked the particles which were the ones which we increased the overdensity of in the initial conditions of that simulation by just choosing the particles which resided in both the target galaxy and the main galaxy. So we essentially increased or made the assembly history of all of the galaxies in a given volume slightly earlier. So the overdensity of this entire region, if you like, was just enhanced. And you might think, okay, well, that sounds like it might be unrealistic. Maybe it's kind of improbable that you get a region of space where the Gaussian random field, you get a draw which was higher than the rest of which was just higher in general in a given region. So we did a few tests by just instead of doing this kind of enhancement where we enhanced the target galaxy and its satellites, we just enhanced the target galaxy and left these satellites all unmodified. And this led to some really interesting results by making this very targeted modification instead of a more sort of broader modification where the assembly history of that whole region was enhanced. What you see is that trend still remains. So we just did a few runs of this. This is just 4 galaxies where you go from early to late now, but instead just only enhancing this target galaxy in the center. And you can see that the general trend still exists. There's some weird departures, like these intermediate galaxies seem to lose their high alpha stars. But really, like at the early times, you can see that they are producing those high alpha stars, just as we saw in the original. But then you also see that these late assemblers look different as well, right? So these galaxies which assembled late are different. And the interesting thing here is that what happens is that when you increase the overdensity of a galaxy in a given region, essentially the overdensity from that galaxy gets kind of transferred into the satellites. So what happens in these cases is that this galaxy, we tried to make the assembly history so late that the assembly history of this galaxy kind of gets pushed onto another galaxy. And so what happens is that a new galaxy in that volume simply becomes the main progenitor, and it has a relatively early assembly history. So you can actually see that in this case, the organic galaxy is just kind of swapping, and then that galaxy merges into the main. So it's kind of interesting. And what this is really telling you is that assembly history is a very complicated beast, and really just to kind of sum things up, you can go back to this kind of plot from the Eagle, and you can see that that scatter really is telling you this as well, right? So this assembly history really is not everything, but really the main thing to take away from this is that when you look at the original modifications we made in terms of that Z quarter value and sigma over I, you can see that they're not that unusual after all. So maybe this isn't such a bad assumption to make, because you would also expect that galaxies which are enhanced in terms of we're having an early assembly history should also be surrounded by a region of space that has an early assembly history. And we're now just looking into ways to sort of quantify this to show that this is not such an improbable draw from the Gaussian random field. So the bottom line here is that, okay, early assembly is a necessary but not sufficient condition for this alpha Fe boundality. So what do the observations say? I'm just going to summarize very quickly. So if you look at ages of things like globular clusters and field stars in the Milky Way, you see that if you look at the in situ and accreted populations, they all are sort of pointing to an early assembly history of the Milky Way. So this is globular clusters in the Milky Way in terms of their age and metallicity from a paper by Diederik Krausen. And you can just see that when you selected galaxies which were kind of in situ to the Milky Way, which we think were formed in the gas of the Milky Way rather than being formed in a satellite and accreted, you can see that they really were very rapidly enriched in terms of their metallicity, right? So in a very short span of age, you really see a very rapid increase in their metallicity relative to these clusters which were accreted in the Gaia and Enceladus merger, which have this kind of much slower evolution in their metallicity at an age. And again, in this paper that I wrote with Josephina Montalban, we measured the ages of stars in the Milky Way's halo with astroseismology. And this just shows the age versus eccentricity plane for those stars that we were able to measure very precise ages for. And you can see so this is a kind of a selection of stars which we think merged with a satellite. But again, you see that most of these stars in the halo, which we think are in situ stars, were formed well before any of these mergers happened, so around 10 to 12 gig years ago. So that really means that the galaxy was really starting to form stars at a very rapid rate at these extremely early times. And we think the absolute scale of these ages is probably just about right when we check with things like eclipsing binaries, for example. And then finally, you can see that the eldest high alpha stars in the Milky Way have very distinct kinematics, right? And this is very consistent with kind of formation in the turbulent gas. So this plot just shows you the ratio of vertical to radial velocity dispersion for populations of stars in the galaxy as a function of age. And I've just colored the points here by the mean orbital radius of these populations. So you can see that these low alpha disk stars, they kind of segregate out in this sigma Z over sigma R, because they were forming in a gas disk that was already kind of dynamically doing things. There were spiral arms. And this gas disk was kind of cool in the center and flared in the outer regions. You can see that's reflected in this kind of enhancement in the sigma Z over sigma R, so these outer disk populations. But the high alpha populations are kind of all very centered in the center of the galaxy, and they all, even as a function of age, have extremely similar sigma Z over sigma R. And the value of this is kind of consistent with simulations where you're forming stars from extremely turbulent gas. So the kinematics of those stars kind of indicates that they formed with that rather than being dynamically heated to where they are today. And I think that kind of tells you something about we see these clumpy galaxies from like HSD, for example, that are forming stars in very turbulent gas. And those are probably in the stage where they're forming these kind of like thick, high alpha populations. So just to kind of finalize things, the next step really is to go and, so we've predicted that this is probably a rare thing in galaxies that look like the Milky Way. And therefore, we want to go and test whether this bimodality is seen in other galaxies. So the next step is I've managed to get observing time somehow on JWST to go and do spectroscopy of giants in M31, where we think we should be able to detect whether there's a bimodality in the alpha Orion plane of the galaxy. And this just shows some simulated data that we made. So we're using here carbon as a proxy for the alpha elements, but it seems that carbon is actually a very good proxy for alpha elements in the Milky Way. And just with mock data, we show that even with relatively, modest precision, we can actually detect whether there's actually two peaks in the distribution of alpha versus I in M31. So this is a really exciting thing. If we find an alpha bimodality there, it might be telling us something interesting. But it's difficult to figure out exactly what that might be telling us yet. So I'm kind of excited to see what we get, but also excited to test whether we'd expect to see a bimodality in a galaxy like M31, which is in the same kind of cosmological environment as the Milky Way, or whether we, by not seeing a bimodality there, does that tell us something interesting? So I really do think this is kind of an interesting metric for galaxies, and understanding that as we go forward will be a really interesting thing. So I'll just leave a summary slide. I've probably gone a bit under time here, but that's probably better for everybody. So I've shown you the Milky Way has this bimodal alpha to IM distribution. I've shown you that cosmological simulations reproduce that feature, and it's linked to an early mass assembly history. I've shown you that when we control for assembly history in those simulations, we can demonstrate that the physical consequences of that mass assembly history help us to understand both how the alpha bimodality can come about, but also how the variance that you see in different galaxies can happen in galaxies just like the Milky Way that have early assembly histories. And yeah, I'll leave it there. Thank you very much.
Thank you very much, Ted. Do we have any questions? Please feel free to unmute yourself and speak out, or type in the chat and I can read it out. Yanqing, did you have a question there?
Hi, Ted. Yeah, I have a question. You mentioned this radial migration and the other scenario you mentioned, which is not the sort of accretion. That one is the alternative, but in this kind of simulation, do they have radial migration, and could that still remain a viable explanation for the bimodality?
Yeah, Yeah, that's a great point, and it's something, it's very important, right? You know, like, so I should have mentioned this before, but like, so a simulation like Eagle, we don't think is really reproducing radial migration like is happening in the Milky Way, right? So the softening dynamics just mean that you can't really sort of see these kind of orbits that get like, you know, elongated and then circularized again at a different radius, right? But what we think is the key is that you know, even to make a model like that radial migration model work, you still have to have this kind of assembly history, right? Because you don't get those high alpha stars unless you have that early assembly history, right? So, the other thing to mention is that we do actually see things like, you know, when you form those high alpha stars in galaxies in Eagle, they start off being kind of very centrally concentrated, and over time they do end up sort of encroaching on like the solar radius of galaxies in Eagle. So you kind of see radial expansion and heating, but I'm not sure whether it's really consistent with radial migration in the real universe. And I think some of these zoom simulations are really interesting in that respect, because they really sort of show, you know, you can start seeing radial migration really happening in those simulations. So that's, I think, an exciting point about why those zoom simulations are really important, actually understanding if there's a link between this mass assembly thing and then also the dynamics of those galaxies is an interesting point. Yeah, maybe that doesn't answer your question, but yeah, the bottom line is that in Eagle, we don't think radial migration in the real sense is really being realized. So yeah, that is a kind of a limitation, but we were able to see this kind of mixing going on, and that's what we kind of attribute to being kind of some sort of proxy for that.
Thanks.
Julio, did you have a question?
Yes, thanks Ted for the wonderful talk. A couple of quick questions. One is, you know, you've done all this with the Eagle code, which has, you know, makes very specific predictions for the, you know, star formation and feedback. And do you think this is really a general result, this early accretion, you know, with alpha enhancements? If you use a different code, for example, would you get something similar? Then I have a second question if this goes quickly enough, I guess.
Yeah, I think it's general, right? So my very basic understanding of things is that this should be general, right? Because we're essentially seeing that, you know, it's all about the density of the gas. So, you know, even if you, I guess that kind of relates back to the subgrid model that you've got, right? But like, in order to get those high alpha stars forming fast enough, you really do have to get the density high enough, right? So unless you were really doing something very differently in the subgrid model, I don't know whether you would not see this effect, right? So it's kind of like the early assembly is what allows you to get those high densities. I guess what could be different depending on the subgrid model you put in is the fraction of galaxies that have this variability. And I'd be really interested to see that. So this is something that I'd love to see. So a lot of the sort of studies that have been done so far looking at this in other simulations don't really look at the like cosmological mass assembly, right? And I'm always intrigued to know whether those galaxies do you know, have this early mass assembly. And it's something that I'm always trying to push people to like add to the papers. Yeah. What was the next? The next bit was.
Yeah, actually, it was kind of related to this. And another clue you have, of course, is that the alpha, high alpha and low alpha, as you call them, we used to call them thick disk and thin disk, of course. Just for those of you who are old enough to remember that terminology, I guess. And it's that the structure is quite different, right? You mentioned that the high alpha are much more centrally concentrated, but also, you know, the vertical structure seems quite different. For example, the vertical height of the thick disk or the high alpha disk, you know, seems to be constant with radius, and that is not the case with the thin disk, which appears to be flared. And that was, you know, people thought it was, you know, the result of a merger or something at the end. Is that still your reckoning of what happened? That, you know, you formed an early disk structure then got really changed a lot by a late accretion of gas and perhaps stars as well that led to the formation of the low alpha stars?
Yeah, you can kind of see this happening in the simulation. It's something that I really want to look at more, and like part of the, you know, the stuff I want to do while I'm here is to really look at things like how for example, I think it's in order to form the thick disks in Eagle, you really have to have like a sort of collapse of gas that forms this very turbulent disk of stars, right? And that really is what gives you the high alpha. And I think that's why the thick disk of the Milky Way also looks like this kind of thick thing, is because it's formed from this early. And I also think that things like the in situ halo populations, like this splash thing that people are saying at the moment, is actually really, I think, the sort of initial star formation you get as the gas kind of cools to form the thick disk. I'm really interested to know, yeah, that's the last bit of the puzzle then, I guess, is really how the gas gets to the thin disk. And this is like, so there's been a lot of work that people have been doing recently, like looking at how gas sort of cools out of the halos and stuff like that, for example, in fire simulations. And I'm really intrigued by all of that. And it's something that I really want to look at. Yeah, so I'm kind of, I don't have a good answer for how the gas would end up getting into but it must happen somehow. I guess you just, like I said, you've kind of got that cool gas reservoir still. You've not kind of like killed off these inflows that you've got. So you've still got some cold gas, access to cold gas after you formed high alpha populations. But I just don't know, yeah, exactly the physics of why that ends up being thin. I guess part of the reason is that the galaxies just, things are less sort of violent at those later stages when you form the thin disk. But yeah, I don't have a good answer for that. So I don't want to go and make random claims that make no sense.
Okay, thanks.
Well, I can make a comment on that actually, right? At least, right, you mentioned that to get the high star formation rates or short timescales, you need to have a lot of gas. That's basically just due to the Koenig-Schmidt relation, right?
Yeah.
If you have to have a high star formation, you have to have high gas. And the reason for that is, well, the time scale is an interesting question, but early on, when you do have a lot of gas in the disk, it's got to be vertically supported. And it's the internal feedback that does that. And the height of the disk really then is just, that's also proportional to the surface density of the disk. So the height of the disk and the star formation rate are intimately connected. Basically, the disk does regulate itself to be at Q equals 1. And if you have a big, the Chume Q parameter, which is a velocity dispersion divided by the surface density of gas. So if you have a big surface density of gas, you're going to have a high sigma. And that's enforced by the feedback, at least in simulations that include that. I mean, in Eagle, it's a little bit different, I think. There is a relation between the two, though.
Yeah.
And then,
I think that's also true in Eagle, Norm. And
yeah, that's what I'm saying. It is true in Eagle.
Yeah. The details are different, but it's true also. But that's not a canonical story. A canonical story is that, the thin disk formed in a very sort of thick disk formed in a very thin structure like the thin disk today, and then was, stars got kicked out by molecular clouds.
I'm just talking about the initial distribution of stars, not what happens after the fact, right? If you think that if you're going to have high star formation rate, you want to have things happen in a short period of time, then you got to have a high surface density, and that disk will be thick to start with. Okay. At lower redshifts, at least like in the Milky Way, and in the simulations you were showing, the gas mass in the disk and the star formation rate were lower at late times, even though you ended up with the same amount of stars, just because you spread out the star formation over a much larger amount of time, right? But those disks are going to be very razor thin because they don't have that much gas in them. So they're going to start out razor thin. Now they also won't thicken as much dynamically because they don't have as much time to thicken, but they'll start out thinner than the same disk with the same mass that assembled and formed early on because you didn't start off with so much gas in the disk. So that'll give you a link between the alpha and the thickness of the disk, even if you don't account for any thickening after the disk evolves.
But then, a lot of the things, like I said, that there's obviously a longer story there about the kinematics, right? But there's kinematics that really look like those stars were formed in that kind of they were formed thick, right? But I think what you're saying is that things have to be, you're only forming stars in the thinnest layer of the gas, or are you saying something different? Am I just misunderstanding?
Well, the gas has got an exponential scale height.
Yeah. Okay, yeah. So high enough density, higher, right? So you can just keep forming stars. Yeah. Okay, that makes sense. Yeah.
We had a few other questions in the chat here. So Terry asked, what kind of stars are you getting spectra for in M31 and how are you selecting them?
Yeah, so we're getting kind of like upper red giant branch stars, and we've just selected based on the fat photometry. So it's like we've just selected a very thin region of the red giant branch. So we know that we've kind of got stars of roughly the same surface gravity and temperature, and then we're just gonna, we've selected essentially just randomly from that set. I'm kind of sure we're going to see if there is a viral, I think we're going to see it just based on the selection that we made, and we're pretty sure we should be able to get pretty highly precise abundances from those stars. Yeah, hopefully that answers that question.
And then I think you already answered Josh's question. Marta asked, in a more general sense, if you could do a wish list which aspects of Eagle would you want to improve that would impact the alpha abundances?
That's a very good question. So many things, right? I guess, so one of the big limitations of a simulation like Eagle is that we don't model very cold phase gas, right? So it's like you have this kind of temperature floor and everything that's sitting on the, I mean, Martin knows this, right? But like, and it's things like that that I really think would allow us to sort of pin this down a bit better, right? Because it's really in the Zoom simulations, you are resolving that cold gas, right? And the subgrid physics is nearly there that you can do that. And I think there's probably a lot more detail in that. And this picture is probably extremely basic and kind of high level, whereas like when you start looking at things like that, I think there's going to be so much more detail and understanding there. And that's really where you get into the steps where you can do things like norms is talking about where you can measure a bit too many parameters and things. So I think that's number one. But there's probably about a million other things that I can do. Yeah.
All right. I think that's a good place to stop. Thank you, everyone. Let's thank our speaker one more time. And I think we can stick around for a discussion if you'd like, but I'll end the recording here.
Peter had his hand up, so it looked like maybe we should wait. I'll wait for that. Thank you very much for the claps.
Peter had a question. But...
Yeah, thanks. So you're going to be looking for bimodality in M31. And what do you already know about this from the globular clusters there? Because you showed some evidence in our galaxy from globular clusters. What do you have that type of information there?
Yeah, so as far as I know, right, the cluster population M31 does look quite different. There's probably people, I think Marta probably knows more about this than I do, but yeah, I think it's slightly different in terms of the fact that it's not as biased old, right? So most of the Milky Way globular clusters look old, and I think a lot of the work on that has shown that this probably means that there was lots of mergers and high pressure gas in the early Milky Way, which was able to form these globular clusters. I think in M31 the age distribution is a lot different. Is that right, Marta?
I think the main issue in M31 is that we don't know what the ages are. So we know that the metallicities are quite different, as in that the globular clusters don't show clear bimodality like we see in the Milky Way. But we are still trying to get their ages because it's quite difficult to do in another galaxy. So yeah, these would be very interesting to see if we wanted to get their ages and some precise element estimation.
Yeah, I think it's like things like that are, I think, important. Like we want to do like as much precursor. Sorry, I think my internet has gone a bit weird, but